Okay, we've just gone through or attempted to go through a example of a hydrostatic problem. So here's some of the key things to remember when you're doing that type of work. First off, draw things to scale. Now for many of you that will probably mean you just do it in AutoCAD or SketchUp. But remember that very often you may have to have a couple of scales on the same plane. So for instance, distance might be 1 unit equals a foot. However, force might be 10 pounds equals a distance unit. I said originally the length might be 1 foot equals 1 drawing unit. Force might be 10 pounds equals 1 drawing unit, and moment might be 100 foot-pounds equals 1 drawing unit. So get used to marking up and notating which scale you're at. You could draft everything 1-to-1, but realistically you'll have a hard time seeing it all in one kind of reasonable look at things. So you do this by just changing the scales and notating. Having things on different layers helps. So you need to draft to scale. You need to very often, at least in your head, move your coordinate system to the spinny point when you define your vectors in the x, y, and z directions. So a coordinate transformation is not necessary to do the work, but it helps mathematically. It makes things a little bit easier. You have to remember what positive and negative is in a 2D plane. Positive coming out of the board is counterclockwise. Clockwise is a negative moment, or a negative k, if you consider z being the direction out of the board. Mark up your coordinate systems for sure. Mark up your coordinate systems, that's a given. Put down all the equations you think you might need. That's a given in terms of your problem solving strategy. Come up with what you expect, perhaps, the sense of to be, but let the mathematics tell you whether your assumptions were originally correct. There's a few things you'll see that many people would resist. One of them would be to always show your reactions in the positive direction, even though you know they're not. I would tell you it's by sticking to these general rules, which are required in terms of having a collaborative environment. You just assume your forces are positive and your moments are positive as you're showing reactions, and then let the negative sign come in from the algebra or the calculation. Remembering that when we're dealing with hydrostatic problems, if we're going to go with a concept of an area under a curve, we have to remember that when we're looking at a 10-foot high wall, you have to think about 1 foot out of the board and then say, well, that's 10 square foot times pounds per square foot gets you pounds. Of course, where do the pounds per square foot come from? They come from the fact that you have a general equation which the change in pressure equals minus the change in elevation times the unit weight of the fluid through which you're quote-unquote traveling. That unit weight is very often 62.4 for hydrostatic problems, though if you're dealing with seawater or something that's, Great Salt Lake water, that number can float up based on specific gravity. Actually, bad pun, but I guess it would float down based on specific gravity. But something can have a specific gravity greater than 1 and be involved in a hydrostatic problem, especially if we look at more and more at marine engineering and that type of thing that we see in Portugal or in the Med regarding capturing the energy of the seawall of the tides. So there's a little non sequitur for you. Some of the most interesting projects in renewable energy are putting large snakes out to the ocean. And when you're dealing with that, you do need to keep track of what the specific gravity of your water is. So get used to the fact that we're going to be dealing very often with 1 foot out of the board, and then if we have a 10-foot wide, more or less, dam gate, then we'll just multiply everything out by 10. You will see in 3 dimensions this becomes an integral, and you can deal with round gates and everything else, but that will be beyond the scope of what we're going to do here, though some of you should start to look at that integration of the reaction, or the fact that force, that the resultant is actually the integral of pressure times the differential area. Finally, most of these, you'll need to know how to do centroids by breaking things into shapes, though realistically that's one of the things we learned last year, that you can use mass prop to determine the centroid, and you'll see it in when we get playing around with Funland or AlgoDo, that it provides the centroid to you very, very easily. But when you come up with a resultant, whether it's the mass resultant, which multiplied by the acceleration due to gravity gives you the weight resultant, you place that resultant force through the centroid acting in the direction of the force. That's the summary. We're doing this just to check that our voice works. We're recording this now directly onto not using a video camera or any of the other tools that don't seem quite to work, as we start to look like a bad old Japanese movie with the sync with the voice and the video. But these senses of hydrostatics being this really good and summative experience at this point. So you've talked about soil pressures in the past, and actually looking forward to when you do look at structures. Hydrostatics, remembering that the area of a triangle is 1/2 base times height, and that its centroid is at a third from the heavy end. There's other ways to get the centroid of a circle or of a triangle. Just draw a line from any vertex to the midpoint of the opposing side. That will also get you the centroid of a triangle. So again, mass prop, great tool. Don't get overly addicted to it doing all of CAD, but really we'll see that for me a graphical method, which would be AutoCAD, would be the way to, I would prefer you addict yourself for calculating centroids. We'll see how this produces. See ya.